Good morning, students, and welcome to this morning's class. Today is a continuation of the series of our classes on time series models. Those of us who have been following our classes closely on YouTube must have seen that we already have classes online that discuss all about the autoregressive model. Beginning from the autoregressive model of order P, autoregressive model of order 1, and then the autoregressive model of what? Of order 2. We equally have had classes discussing the moving average models, beginning from moving average model of order Q, moving average model of what? Of order 1, and then the moving average model of what? Of order 2. Today is a combination of the autoregressive model and then the moving average model to give us what is called the ARMA model. So we want to begin to look at ARMA model today. And we are going to look at this ARMA model by first of all trying to understand what ARMA model is, trying to know how to write the ARMA model, how to drive the mean of the ARMA model, how to drive the variance of the ARMA model, and then how to drive the autocovariance of the ARMA model. Now, the AR model states that the current value of a time series depends on the previous values of that particular series. That is the definition of of the AR model. The definition of the moving average model states that the current value of a series or a time series depends on the previous error term or white noise of that particular series. But we are saying that in some real life situations, we might come to a series where the current value of a series depends both on the previous value and then on the previous error terms. A situation whereby the current value of a series depends both on the previous value of of the series and then on the previous value of the white noise of of the series. We no longer have autoregressive, we no longer have moving average. What we now have is what we call the autoregressive moving average models, which is called in a short form ARMA model. So we want to look at the order of autoregressive model is always written as P, and then the order of moving average is always written as what? As Q. Therefore, this ARMA model combines both the order of what? AR and then both the order of what? Of MA. Remember that AR is written as this: AR of order P, called autoregressive model of order P. MA is written as what? MA of order Q, called the moving average model of what? Of order Q. This ARMA combines both AR and MA. The first part here, AR, is talking about the autoregressive. The second part here, MA, is talking about what? The moving average. So ARMA combines both this and this. And then the ARMA model will now be written as this: A R M A of order P Q. So called the autoregressive moving average model of order P Q. This P is talking about the order of the autoregressive terms, and then this Q is talking about the order of the moving average terms. So we now ask ourselves, how do we write the model of this autoregressive moving average of order PQ? It is written this way. It is given as what? Y of t. And let y of t be the time series observation at this current moment, or the current time series observation. This will be given as, we have what we call phi 0 plus, we have what we call phi 1 y of t minus 1 plus phi what 2 y of what t minus 2 plus plus we have phi what p y of what t minus what minus p. Then we now say plus. We have a of what t plus theta 1 a of t minus 1 plus theta what 2 a of t minus what 2 to plus we have theta what q a of what t minus what q. Now if they ask you to write the model of autoregressive moving average model of order PQ, it is written this way. And I want to make something clear here. This phi 0 is what we call the constant of this model. It is the constant of the model. Then from this phi 1 up to this phi p is the autoregressive terms in this ARMA model. While from this theta 1 down to this theta q is what we call the moving average terms in this model. This is always the white noise that is always included in model, where we now say that this white noise A of t follows what? Normal with mean 0 and variance sigma squared of what? Of A. And with this, you have written what is called the ARMA PQ. Our interest this morning is going to be centered on the ARMA 1-1. That is, where the P is 1 and then the Q is what? Is 1. By that, we now continue to go and write the model for ARMA 1-1, derive the mean for ARMA 1-1, derive the variance of ARMA 1-1, and derive the autocovariance function of ARMA 1-1. So you are now going to see what we are going to do here. Then if I want to write the ARMA 1-1, I will now write what? A, R, M, A. That is ARMA 1 and 1. So we say this will be given as, I will now say that this will be given as y of t is given as phi 0. Here, there are p autoregressive terms 1, 2 up to p. But now we are interested only in one autoregressive term, which is this first one, plus phi 1 y of t minus what? 1 plus. We already arrive at this a of t, a of what? T. We are interested in only one moving average terms. And we have up to what? Q moving average terms here. But we are interested in the first one. So we have plus. We have theta 1 a of t minus 1. We say where this a of t follows what? Normal with mean 0 and variance sigma squared of what? Of a. With this becomes what we call the model of ARMA 1-1. So you are going to permit me to kill it. However, at times we have a situation where this our constant is 0. And if this constant becomes 0 now, we can equally write the model this way, that this becomes y of t will be given as phi 1 y of t minus 1 plus a of what? T plus theta 1 a of t minus 1. Where this a of what? T follows what? Normal with mean 0 and variance sigma squared of what? Of a. So when we see this and we see this, we should know that in this second model, our constant is 0. But in the first model, constant can be any other value apart from what? 0. So you permit me now to clean the board while we go over to driving the mean, since we have seen how to write what? The model. ARMA 1-1. So Our ARMA 11, ARMA 11, our ARMA 11, ARMA 1, 1. The model is written as this. The first one, the model will be written as this. Y of t is given as phi 0 plus. We have what? Phi 1 y of t minus 1 plus a of t plus theta 1 a of t minus 1, such that our a of t follows normal with mean 0 and variance sigma squared of what? Of a. Okay? Then, where these are constants is contained in the model, and our constant is not 0. So we can equally write the model where we assume that this constant is 0, and then the model will be written as what? Y of t is given as phi 1 y of t minus 1 plus a of t plus what? Theta 1 a of t minus 1, such that our a of t still follows what? Normal with mean 0 and variance sigma squared of what? Of a. So the first thing here is we have written the model. This is how to write the model of ARMA 11. We want to go and look at how to obtain the mean of ARMA 11. And of course, when we talk about mean, we are talking about the expected value of the ARMA 11 model. So if we talk about the mean, what we are going to do is to take the expectation of both sides of what? Of the model. So we talk about the mean of the model, which is that number 2 there, the mean or the expected value of the model, expected value of the model. What am I going to do? I will quickly say that my y of t here, y of t is given as what? Phi 0 plus what? Phi 1 y of t minus 1 plus a of what? T, then plus what? Theta 1 a of t minus 1. Okay? I will take expectation of both sides. So it becomes e of y of what? T is given as what? E of phi what? 1 plus phi 0, plus phi 1 y of t minus 1 plus a of t plus theta 1 a of t minus 1, close the brackets. I am now going to use this expectation sign to open the what? The brackets. And what I'm going to have becomes, this is e of phi 1 plus. Here becomes what? E of what? Phi 1 y of t minus 1 plus e of what? A of what? T plus. We have what? E of what? Theta 1 a of t minus 1. You close the brackets. Now, of course, we know that expected value of a constant is a constant. So this thing becomes what? Phi 0. This is phi 0. Then plus. Whenever we have a constant inside expected value, that constant can be brought outside. So I have phi 1 e of what? Y of t minus 1, close the bracket, plus. Expected value of white noise, or what we call the error term, we have been told that the expected value follows, that the error term follows a normal with mean 0. And expected value, of course, is what we call the mean. So this quantity becomes what? 0 plus. Constant is inside, so we have what we call theta 1 e of what? A of t minus 1. We close the bracket. Now, let us say that the expected value of y of t is what we call mu of y. That is the mean of what? Of y, mu of y. So here, e of y of t, let us write it as what? Mu of y. Mu of y. This is equal to what? Phi naught plus. Now, for stationarity, the mean of the series is constant over time. And if it is constant over time, it implies that the mean of the series at y of t is the same thing as the mean of the series at y of t minus 1. Because when you talk about stationarity, which of course we are discussing stationary models, you are saying that the mean is constant over time. And if the mean is constant over time, the mean at y of t is the same thing as the mean at y of t minus 1. So the mean here now is equally going to be, here I have my what? My phi 1. Here now is now going to be what? Mu of y plus. Here is already 0 plus. Here is already what? Theta what? 1 multiplied by. We are equally discussing what is called what? The constant what? Stationarity. And if the mean of the error term at t is 0, even the mean at t minus 1 will equally be what? 0. So here becomes multiplied by 0. So from here to here becomes 0. What we have left here is this. So we have what? Mu of y, which is what I have here, is given as what? Phi 0 plus. What I have here becomes what? Phi 1 mu of y. So by a way of collecting like terms, those that contains mu of y, this one coming over here, I have mu of y minus phi 1 mu of y. This is given as what? Phi 0. Factorizing this mu of y out, I have mu of what? Y, open a bracket, 1 minus phi 1, then this equals what? Phi 0. And making this mu of y subject to formula now, it becomes that mu of y will now be given as what? Phi 0 all over. We have 1 minus what? Phi 1. So, and this thing now becomes what we call the mean, or what we call the expected value of the model of ARMA 1-1. And we are going to give a condition here. A condition there is that the absolute value of phi 1 is always less than 1 for the stationarity of AR of order 1 model, since this phi 1 is the parameter of the AR of order 1 model. So this is how to drive the mean of ARMA 1-1. Okay? When you want to drive the mean, we encourage you that you keep the constant in the model. But when we want to drive the variance now, drive the autocovariance now, we are going to let go of the constant, knowing full well that the variance of a constant is 0. So you permit me to clean this while we talk about now the variance of ARMA 1-1. And we are going to use our second model. So permit me to clean here. Okay, so when we talk about the variance of ARMA 1-1, which is the number 3 thing we are looking there, we are talking about the variance. So if we talk about the variance, what we are equally going to do is to take the variance of both sides, remembering one thing, that when we have the variance, if we have the variance, permit me to clean up to here. If we have two random variables, x and y, where we have information that these random variable x and y are not independent of each other. They are not independent of each other. We have that var of x plus what y is given as what? We have what? var of x plus var of what? Of y, then plus two covariance of what? X, comma what? Y. This is how to express this when you want to write this kind of a thing. Okay. So in that case now, what I'm going to do now is I have a model, and that model is talking about what? Y of t is given as what? Phi 1, y of t minus 1, plus what? We have a A of what? T plus theta 1 A of t minus 1. And I have information that A of t follows normal with mean 0 and variance sigma squared of what? Of A. So by taking variance of both sides, what I'm going to do now becomes what? var of what? Y of t will be given as what? var. I will take the variance of each of the terms like I did here before I begin to consider the covariance terms. So by taking the variance of this place now, I have var of phi 1 y of what? T minus 1 plus. I'll take the variance of this one. var of A of what? T plus. I'll take the variance of this one, which is var of what? Theta 1 A of t minus 1. So I'm done taking the variance of each of the terms. I begin to consider the covariance terms. So I will now say plus 2. I will now take the covariance of this and this. And of course, there is a constant here called phi 1. So I will now write that phi 1 outside now. So 2 phi 1 covariance of y of t and A of t. So I have y of t minus 1, comma, A of what? T. Close it. I will now take the covariance term of this quantity and this quantity. This one contains phi 1, this one contains theta 1. So I will now write plus 2 phi 1 theta 1 covariance of y of t minus 1 and then A of t minus 1. We have what? Y of t minus 1, comma, A of t minus 1. Close it. Plus. I am now going to take the covariance term of the last base, which is this and this. And I will now have 2. I have theta 1 covariance of, I have A of t, comma, A of t minus 1. Close the bracket. Now, what am I going to do now? I will now go ahead now to simplify this bracket, which is now going to be that my var of what? Y of t will now be given as, when a constant comes outside the variance sign, that constant gets squared. So what I'm going to have here becomes what? Phi 1 all squared var of y of t minus 1 plus. The variance of the error term has been given to us as sigma squared of A. So I have what? Sigma squared of what? A plus. I will now come over here. Constant comes outside. So I have what? Theta 1 what? Squared. Then I now have what? Variance of what? I have var of what? A of t minus 1. Close the bracket. Plus. Then I will now come here. We are going to pay attention here. If you express this y of t minus 1, there is no term in y of t minus 1 that contains what? A of t. Okay? Assuming now, because look at now, if I express y of t minus 1, what I'm going to have here becomes what? I have that y of t minus 1 is given as, I have a phi 1 y of t minus what? 2, then plus. I have what? A of t minus 1 plus. I have theta 1 A of t minus what? 2. So when you are given y of t, it is expressed like this. But when you are given y of t minus 1, you are going to express it like this one. Here is y of t, but this term here is t minus 1. This term here is t, and this term here is t minus 1. So this time around, you are giving t minus 1. So you still subtract that one you subtracted to get here. You have t minus 2. You subtract equally because here is what? T, and here is t. So you now have A of t minus 1, which is exactly what you have here. Then you subtract 1 now to get this one. Then if you come here now and you begin to compare each of these terms with this A of t, this one here does not have A of t. This one does not have A of t. This one does not have A of t. So the covariance term here now becomes what? 0. Because there is no terms now that have exactly the same value there. So, which means I have now 0. Because when this covariance, which is 0 multiplied by this, everything is 0 plus. Then when I come to this one, this is y of t minus 1. I will now compare each of the terms here. if I compare each of the terms here, I now find out that there is A of t minus 1 and there is A of t minus 1. So the covariance is not going to be 0. So I will write it that way. 2 phi 1 theta 1 covariance of A of t minus 1 comma A of t minus 1. Since the whole of this, the only place where we are interested that we have the same value with this is this. Then we now say plus. When we come to this one, there is nothing to express. This is A of t, this is A of t minus 1. So they don't contain anything that is common. So it becomes what? 0. So we say plus 0. So this thing becomes what? var of y of t is given as, we now have what we call phi 1 all squared v of y of t minus 1 plus sigma squared of what? A plus. We have theta 1 all squared, then var of A of t minus 1 is, if we have a stationary model, the mean is constant, the variance is constant over time. So if the variance of A of t is sigma squared what? Of A, even the variance of A of t minus 1 is going to be sigma squared of A. Sigma squared of A plus. Here is 0, I will now come here. Covariance of this and this is the variance of this. Each time you have covariance of x and x, the answer is variance of x. Covariance of y and y, variance of y. Here is covariance of A of t minus 1 and A of t. So it is variance of A of t minus 1. And the variance of A of t minus 1 is sigma squared of A. So I have 2 phi 1 theta 1 sigma squared of what? Of A. So what am I going to do? Let the variance of y of t be sigma squared of what? Y. This will now be what? Phi 1 all squared. Here is equally going to be sigma squared of what? Y, because of a constant variance. Then plus. We have sigma squared of what? Of A plus. Here becomes this one becomes theta 1 all squared, sigma squared of what? Of A plus 2 phi 1 theta 1 sigma squared of what? Of A. Let me bring this one that have y over here and retain the other one the other side, so that what I'm going to have now becomes what? We have a sigma squared of y minus phi 1 all squared, sigma squared of what? 1 y, then equals sigma squared of what? Of A plus theta 1 all squared. We have a sigma squared of what? Of A plus 2 phi 1 theta 1 sigma squared of what? Of A. I will now factor common terms, which is sigma squared of what? Y into 1 minus what? We have phi 1 all squared, close it, this equals. I will equally factor common terms here, which is open a bracket. Here is 1 plus theta 1 all squared plus what? 2 phi 1 theta 1 close the bracket, sigma squared of what? Of A. I will now make this sigma squared of y a subject of formula. I will now say that sigma squared of what? Of y will now be given as 1 plus theta 1 all squared plus 2 phi 1 theta 1, then close the bracket, sigma squared of what? Of A, all over 1 minus phi 1 all squared. And by this, we have obtained the variance of ARMA 1-1 model. With that condition still holds, the absolute value of phi 1 must be less than what? 1. So if you are asked to obtain the variance of ARMA 1-1, this is the process you are going to follow. And may I remind you that, of course, when you talk about variance of a model, you are talking about the autocovariance of that model at lag 0. So some people can equally write that this, our sigma squared of y, is what we call gamma 0. So when we begin to call it gamma 0, autocovariance at lag 0, understand what we mean by that. So quickly permit me to clean this while we talk about what the autocovariance. So permit me to clean here. So in a situation whereby you are given the values of theta 1, given the value of phi 1, giving the value of the variance of the error term, and you are told to numerically evaluate the variance of what of ARMA 11, you can do it. The same thing applies with the mean that we already had discussed, that when you are given the value of a constant and you are given the value of what of the autoregressive parameter, the phi 1, you will be able to obtain the mean of the ARMA 11 model. Remembering that the mean of ARMA 11 model is mu of y is given as a phi 0 all over 1 minus phi 1. So the moment you know the value of phi 0 and you know the value of phi 1, you can numerically evaluate the value of the mean of the ARMA 11 model. Permit me to bring down my curtain to avoid the reflection of light. So we are now going to discuss about the autocovariance. So quickly permit me to clean here. Okay. When we talk about the autocovariance, it has a step of obtaining it. The step of obtaining it is we first of all multiply both sides of what of the equation with y of t minus k before we now take expectation, or what we call expected value. So if I want to do that, we quickly remind ourselves that the model is, we are talking about now the autocovariance, which is the number 14 that we are discussing here, the autocovariance. Autocovariance. So what we do is to quickly write the model, and of course we know that the model we are discussing is y of t is given as a phi 1 y of t minus 1 plus we have what is called the a of t plus theta 1 a of t minus 1. And our a of t follows what? Normal, mean 0, and variance sigma squared of what? Of a. So we first of all multiply this model by y of t minus k. So I have y of t multiplied by y of t minus k. This equals, I will now use that thing to multiply here equally, which is phi 1 y of t minus 1 plus a of what of t plus theta 1 a of t minus 1, all multiplied by what? Y of t minus what? K. So what you are going to do now is to open the bracket by allowing this k to come inside, which becomes that my y of t multiplied by y of t minus k is minus k is given as, when this one comes here, you have phi 1 y of t minus 1 multiplied by y of t minus k plus. You have what? A of t multiplied by what? Y of t minus k. Then you have plus. Then you now have what? Your theta 1 a of t minus 1 multiplied by y of t minus what? K. At this point in time, you are going to say when k is equals to 1. So you are now discussing the autocovariance at lag 1. So when k is equals to 1, when k is equals to 1, what you are going to have here becomes what? Y of t multiplied by y of t minus 1. This is equal, because k has become 1. This is equals to phi 1 y of t minus 1, which is this one. You come here, multiply by, you have what? Y of t minus equally 1, because k has become 1. Then plus, you come here, a of t multiplied by what? You have a y of t minus 1 plus. You come over here, theta 1, then a of t minus 1 multiplied by y of t minus 1. At this point in time, you are going to take expected value of both sides. So by taking expected value, you have e of y of t multiplied by y of t minus 1 is given as, this phi can come outside, phi 1, you have e of y of t minus 1 multiplied by y of t minus 1 plus. Then you have e of a of t multiplied by, then you have what? Y of t minus what? 1. Close it. Then plus. You have your theta 1 e of a of t minus 1 and y of t minus 1. You close the bracket. Now, of course, when you take expected value of a y of t and y of t minus 1, we call it gamma 1. That is autocovariance at lag 1. So this becomes what? Our gamma 1. This is equals to, here is our phi 1. When you take expected value of a two random variable, and that two random variables are the same thing, you are talking exactly about the variance of that model. That is expected value of x and x is what we call variance of x. And that's exactly what I have here. So this expected value of y of t minus 1 and y of t minus 1 is variance of y of t minus 1. And we know that the variance of y of t minus 1 ab initio, we have proved it. And that's what we call the gamma 0, autocovariance at gamma 0. So this thing becomes what we call gamma 0. Okay? Then plus. Of course, when we express this like we express it here, we find out there is no term here that contains a of t. So this expected value now becomes what? 0. Okay? So here we have what? 0 plus. And then when we come here, of course, when we now expand, we see a of t minus 1 and we see a of t minus 1 here. So the whole of this y of t minus 1 will just be replaced with a of t minus 1. And when it is replaced now, we are now talking about expected value of a of t minus 1 and a of t minus 1. That becomes the variance of a of t minus 1. So I have here to be what? Theta 1, then sigma squared of what? Of a. So the whole of things here becomes what we call gamma 1 equals, we have phi 1 gamma 0 plus what? We have theta 1 sigma what? Squared of what? Of a. And we already have proved the variance, which is gamma 0. And we can remember the value of that variance we proved. So we just come here and replace it. If I have not forgotten, the variance we proved the other time was sigma squared of y, which is equals to gamma 0, is given as, I think I remember that we had something like 1 plus theta 1 all squared plus what? 2 phi 1 theta 1 by bracket sigma squared of what? Of a all over 1 minus phi 1 squared. If I haven't forgotten, this is the value of that our variance. So what we are going to do is to carry this and put in place of this y0, gamma 0. So we have that our gamma 1 will be given as, we have phi 1, you open a bracket, you put this value there, you open this kind of bracket, and then you put this value 1 plus theta 1 all squared plus 2 phi 1 theta 1, close the bracket, sigma squared of what? Of a all over 1 minus what? Phi 1 all squared. You close the bracket. But you still have this term remaining. So you have plus, you have theta 1 sigma squared of what? Of a. So when you are asked to prove the autocovariance term of ARMA 1 at lag 1, this is what you are going to have. At lag 1, this is the value you are going to have. So we want to quickly go and look at what happens at lag 2, what happens at what? At lag 3 down the line, so we can make a conclusive statement about the autocovariance. So permit me to clean here. I do not want to believe that you have had any challenge yet. So we now say when k is equals to 2 now, we are now going to say when k is equals 2. So when k becomes what? 2, what is going to happen that here is going to be 2. So we have y of t multiplied by y of t minus 2. This is given as a phi 1 y of t minus 1 multiplied by y of t minus what? 2 plus. Here becomes what? A of t multiplied by y of t minus what? 2 plus. Here becomes what? Theta 1 a of t minus 1 multiplied by y of t minus what? 2. Then we now take expected value of both sides, which becomes e of y of t multiplied by y of t minus 2, close it. This is what? Phi 1 e of y of t minus 1 multiplied by y of t minus what? 2 plus. We have e of a of t multiplied by what? Y of t minus 2 plus. We now come to this one, theta 1 e of a of t minus 1 multiplied by y of t minus what? 2. We close the bracket. And then we return back here. Whenever we are taking expected value of y of t and y of t minus 2, we call it exactly what is called our gamma 2. So here becomes gamma what? 2. Autocovariance at lag 2. This is given as, we come here. Here is my phi 1. We are taking expected value of t minus 1 and t minus 2. So this quantity here is autocovariance at lag 1. Okay, so we have what is called gamma 1 plus. Then we come here. When you express y of t minus 2 using this guideline, there will be no term that contains a of t. So this quantity becomes 0. When you equally now express this y of t minus 2 using this idea or principle, there will be no term that contains a of t minus 1. So this quantity becomes what? 0. So you are left with that gamma what 2 is given as phi 1 gamma 1. And you know that you earlier had proved your gamma 1. But first of all, keep it now. Let us now go and look at when k becomes what? 2. 3, sorry. When k becomes 3, what we are going to have is now when k is equals to 3. When I come here, I'll be replacing 3 these places. I'll be replacing 3 these places. So what I have now becomes, sorry for the light has gone off, becomes expected value of y of t dot y of t minus 3 plus. Here becomes a phi 1 e of what? Y of t minus 1 and y of t minus what? 3. Close it. Plus. I'm here. E of a of t multiplied by y of t minus 3 plus. I am here, which is theta 1. We have e of a of t minus 1 multiplied by y of t minus what? 3. So we now know quite alright that here now we are talking about gamma 3, autocovariance at lag 3. So we now come here, this equals, please, equals, this equals equality sign. So we now come here, what we have here is what? Phi 1. This thing here is what we call our gamma 2. So we have gamma what? 2. When you express this thing using that principle, this term becomes 0. When you express this thing, there is no term in it that contains here. This quantity becomes 0. So you have now that gamma 3 is equals to phi 1 gamma 2. You have that gamma 3 is equals to phi 1 gamma what? 2. But you know that your gamma 2 is phi 1 gamma 1. So you can say that your gamma 3 will now be given as a phi 1, which is here, multiplied by gamma 2 is phi 1 gamma 1. So you have a phi 1 gamma 1. So which becomes a gamma what 3 will now be phi 1 all raised to power 2 gamma what 1. And if we can establish that something like this exists, what I have here is 3, what I have here is 2, which means something like a 3 minus 1. So I can say that gamma 3 is given as a phi 1 raised to power 3 minus 1 gamma 1. And if this is true, which of course is true, it implies that my gamma k will now be given as phi 1 raised to power k minus 1, then gamma 1. This condition will continue to apply as long as our k here is greater than or equal to what? 2. It is once it is greater than or equal to 2, because you remember the value when we had about the gamma 1, you remember the value when we had our gamma 2 and then the rest of them. When we had all of those things now, so here we say that k is greater than or equal to what? 2. From k being greater than or equal to 2 now, we now have something like this as what we call the autocovariance function of ARMA 11. Autocovariance function of ARMA 11. Thank you very much for your audience so far. We really have taken your time, but then it is for good because it requires detailed explanations and clarification before somebody can navigate ways around obtaining the mean, the variance, and the autocovariance function of ARMA 11. Stay connected. Our next class will still be deepening our discussion on ARMA 11 and ARMA model in general.